so everything went down. So there's nothing I can do about it. All right, so let us continue where we left off the last time. So we will. Okay, so here we are. All right, okay. All right, so let us get this over with. We are almost there. Okay, so I guess here, so before we were cut off, so we have already generated this table. All you have to do now is just to transfer this point to your polar plot. Make sure that before you start your second test, make sure that you have a polar plot with you. So now we can now just transfer this. This is, of course, the first point. You cannot transfer the first point, even though the angle is -90, but the magnitude, the radius is infinite. So it is very far away from the origin. So you cannot start with the first point. You can now transfer the first point at an angle of -1, almost -50, with a radius of 1.3. And of course, you need to prepare your graph paper. Okay, so here, look at the magnitude 1.3. So now here there is magnitude 1 and 2. It should be enough. So this is my first point. So this is our first point. A magnitude of 1.37 or 1.4 at an angle of -150. So if you have your graph paper ready and this angle of -150, you go clockwise from your right, going down 149 degrees, and then measure 1.4. So that's your first point, and then you transfer all the rest of your point. So 1, 2, 3, 4, 5 points. The first point, because the magnitude is infinite, then you cannot have your first point. So now this is now become your Nyquist diagram. From omega equals 0 to omega is equal to infinity. When your omega is equal to infinity, the magnitude is 0. So and the angle is negative 240. Negative 270. Negative 270 is vertically upward. So you are coming down. You're approaching this vertical line. So that is going to be your Nyquist diagram. And then the question asks whether the system is stable. For a stable system, you want to, if the system is stable, you want to compute the gain and phase margin. Now, look at point -1. So this is point -1. Since our Nyquist diagram crosses to the right of -1, so therefore now we say that the system is stable. The system is stable since -1 is on the left of the curve, or the curve is on the right of -1 is the same thing. So now we say that the system is stable. So for a stable system now, if the system is stable, then we can now compute the gain and phase margin. If you draw this diagram, to scale, you can just measure this angle. So draw a circle of radius 1. So radius 1, you draw a circle of radius 1. So this is 1. The distance from the origin to that point is 1. And then you can measure that angle. That angle is now our phase margin. You can also measure x to scale. So there is -1, there's 0.5. You can measure x, and then you can get the gain margin. Okay. The value of x and gamma can be measured from the diagram. So roughly here, I get x is equal to 0.4, and then you get the gain margin of 2.5, and then the phase margin, when I measure that, approximately 23. So in your test, measurement from the diagram that you have drawn is acceptable. So it can be accepted this measurement, this accuracy is acceptable. Reading directly from your diagram. You can also compute using the definition of gain margin, phase crossover frequency and the gain crossover frequency. See, you can compute the gain crossover frequency, you can compute the phase crossover frequency, and then from there you can compute the gain and phase margin. So I did that as well. The gain margin and the phase margin can also be computed using the phase crossover frequency and the gain crossover frequency. So your first step is to determine what is the phase crossover frequency, what is the gain crossover frequency. So from the definition, at phase crossover frequency, the phase angle is -90. So you use this expression for your phase angle. So the expression for your phase angle, this is phase angle. So when the phase angle is 180 or -180, the frequency at that particular point is the phase crossover frequency. When the magnitude is 1, so the frequency at that particular point is the gain crossover frequency. So using that definition, you can compute the phase margin and the phase crossover frequency and the gain crossover frequency. The phase crossover frequency is frequency when the phase angle is -180. And then from there, you can now compute the gain margin. Once you get this phase crossover frequency, which is 10, so all you need to do to compute the gain margin is to compute the magnitude at that particular point, at this particular frequency, and then now 1 over that is your gain margin. Okay, so now it's 1 over the magnitude. Substitute frequency is equal to phase crossover frequency, and then of course you get 0.4, which is exactly what we have read from the graph. So that's 0.4, that's 0.5. So amazingly that you get here the magnitude at 10 is 0.4, and then from there you can now compute the gain margin is equal to 0.5. Phase margin is computed using the gain crossover frequency. So first you need to compute the gain crossover frequency from the definition. So the gain crossover frequency is when the gain is equal to 1. So you substitute omega g in your expression to compute the gain, and then from there you can solve from the gain crossover frequency. And now again, this is not an easy equation to solve. See, this is also not an easy equation to solve. Omega p here, no, this is not easy to solve. This is called a transcendent equation. If you already taken your applied numerical method, you can use any method that you can that is discussed to find the roots of an equation. But see, but you can use trial and error. You can help from this diagram. You already know that. So this is when the phase angle is 180 here. So that is going to be your phase crossover frequency. And then look at the gain. So the gain crossover frequency must be between these 5 and 7. So between 1.3 to 0.7. So your gain crossover frequency is somewhere between 5 and 7. You can use that information to solve this, maybe by trial and error, I guess. You can use this trial and error, and then now you get your gain crossover frequency. Once you get your gain crossover frequency, all you have to do now to compute the phase margin is 180 plus the phase angle at that particular frequency, and then you can now compute 22.5. Again, this is not really attractive for you to solve this equation in your test. So this is not really attractive to solve, but somehow sometimes you have to. If you must, you can do the computation, but I suggest you just read directly from the diagram. You're going to save a lot of time by doing that. You just draw your Nyquist diagram to scale. So read your phase margin and gain margin directly from the diagram. Okay, so do you have any question now? If you have any question, then you can type your question in the chat box, or you can ask your question verbally. Okay, so looks like everything is good. So this is the first type of question. This is I call the student-friendly question. A control system is designed for you. Given a control system, just evaluate whatever quantities that is asked in the question. So the next example that we are going to discuss is the design type of question. Okay, so this is the type of question that you're going to see in your final or something, maybe in your second test as well. See, a proportional control system is given as follows. So you have this feedback control system with a proportional controller gain k. It is not given. The value of k is not given. So you're going to be given a specification, and then you need to determine what is the value of k such that the specification is met. So this is quite a nasty question for you to solve in the exam, because you have limited amount of time. Yeah, so anyway, so this is not a problem. This is not really a big problem. Okay, so given that, so this is now what you need to do. The question may ask you to draw the Nyquist diagram for k is equal to 1. Okay, and then determine the maximum value of k for stability. You want to, so this question wants to know how big can you design your controller, how big is the value of k that you can have until you reach instability. So there's a first task. What is the range of k that you can have so that the system is still stable? And this part C is even nastier still. So determine the value of k such that the phase margin is 30 degrees. 30 degrees is already in the range of guideline that is going to have a satisfactory performance. So A, B, C. So this is the type of question that you're going to face in your second test. If you can do this, then you should be fine. Okay, it should be good. You just go over this example, and then voila, you'll be ready for your second test. All right, so to draw the Nyquist diagram for k is equal to 1, all you need is the open loop transfer function. So this is already the open loop transfer function. So for k is equal to 1, and then you get the open loop transfer function for k is equal to 1, which is just 10 s divided by s, and then you have a repeated root here, 1 plus 0.1 s squared. So there's two terms there. Okay, so get the open loop transfer function, and then replace s with j omega, and then you're going to have expression for magnitude and the phase angle. See, the magnitude of 10 is just 10. The magnitude of omega is just omega. You have two terms here. So square root of the real part plus imaginary part square, and then you have a repeated root. So basically, you multiply these two terms together, or you have this easy expression 10 divided by omega multiplied by 1 plus 0.1 omega squared. That's it. Because this is square root and square root, double square root here. When you multiply, it's going to be square, and that's going to go away. So this is expression for your magnitude, and then this is your expression for your phase angle. The phase angle for 10 is 0, minus 90 for 1 over s, and then minus arc tangent of 0.1 omega, and you have a second term, and then this is just going to be 2 times that. So this is expression for magnitude, and this is expression for phase angle. And then you only have one time constant. Your time constant is 0.1, so 1 over that is 10. So that's all you have to work with to select your value of frequency. So 1 over 0.1 is 10. So I select a few more points from 0 to infinity. So I select 3, 5, and 20. You can see that when your magnitude is smaller than 0.1, you can stop. So don't go any. When you increase your frequency, when the magnitude is getting smaller than 0.1, you can stop there. There's no, you cannot draw accuracy any less than 0.1. So you compute your phase angle. So this is now your point. Okay, here's your point from 0 to infinity. So you can see that the biggest magnitude is 3. So now if you look at my scale here, there's one, then it should be -1, -3. So this is the real axis, this is imaginary axis. Now you can now transfer the point. Again, you can now transfer your point. If the question asks you for your phase margin and gain margin, you can now see the phase margin is around 22 degrees and the gain margin is about 1.0.5, which is equal to 2. So the gain margin is 20, 1 over 0. This is not 20, right? Okay, what the hell is that? This is not 20. 1 over 0.5 is 2, I guess. Make a correction. This is not correct. 1 over 0.5. That's not 20. It's 2. And the phase angle, the phase margin is 22. So that is the first part of the question, part A. Draw the Nyquist diagram for k is equal to 1. And then you want to know the maximum value of k for stability. So if you look closely at this expression, the phase angle is not a function of k. K is nowhere to be found. So k, if you increase the value of k, all you do is increase the value of your magnitude. So when you increase the value of k, all you do is multiply this this magnitude. The phase angle is not going to change when you change the value of k. So this is for a value of k is equal to 1. When your k is equal to 2, you just multiply the whole thing by 2, the magnitude by 2, but the phase angle stays the same. So how much can you multiply this until your gain margin is going to be equal to 1? So here you already have 0.5. If you can only multiply by 2. If you multiply this by 2, and then your x is going to be equal to 1, so that is already at the maximum value of k that you can have before become unstable. Okay, so again, so you can compute the gain and phase margin. Okay, so now the same way that previous equation. So we have answered this. So we're going to go to part B. So the phase crossover frequency is independent of k. It's not a function of k. So the phase crossover frequency is going to be stays the same. The phase angle is not a function of the gain k. It's not going to change. The phase angle is not going to change. So the phase crossover frequency is going to stay 10. Why do I say the phase crossover frequency is equal to 10? Because when frequency is equal to phase crossover frequency, the phase margin, the phase angle is going to be equal to 180. So now we have this phase crossover frequency is equal to 10. So therefore now we have this gain margin is equal to 2. So the gain margin is apparently is how much you can increase the value of your controller before it become unstable. So your phase crossover frequency is 10. So the critical gain for stability is when x is equal to 1. So you substitute this phase crossover frequency in your gain, and then you can now compute the critical gain for stability, which is equal to 2. So your phase margin will tell you information that this is how much you can multiply your magnitude before you reach unstability. So the critical gain before stability is equal to 2. Okay, so the critical value of your controller gain is now, you can now compute, is 1 over 0.5, which is equal to 2. So we can do this from the fact that the phase crossover frequency is independent of the value of the gain k. So now you can now answer this part B of the question. And part C of the question is, you want to know what is the value of k such that the phase margin is equal to 30. So our phase margin now is equal to 22. So this is not satisfactory. We want the phase margin to be greater than 30 degrees. So you know that when k is equal to 1, the phase margin is equal to 22. When k is equal to 2, your phase margin is 0. 0 meaning that you're already at marginal stability. So to be able to fulfill this criteria, phase margin is equal to 30, you need to decrease your k. Your k must be smaller than 1. Only then you can meet this criteria. So you can now compute that. So let's go down to part C. Okay. So we want the phase margin to be equal to 30. From there, you can now compute the gain crossover frequency. The gain crossover frequency use the expression for phase margin. So phase margin is equal to 180 plus the phase angle at gain crossover frequency. Again, this is if you have more terms here, it is not an easy equation to solve. But since in this case we only have one arctangent here, you can easily solve for gain crossover frequency. So substitute that, knowing the fact that at gain crossover frequency, the value of gain is equal to 1. So substitute that again, this frequency in your magnitude expression. Now you can now compute the value of gain k to fulfill this phase margin is equal to 30. So when your k is equal to, you can now solve this. This is a very easy equation to solve, and then you get the value of k is equal to 0.775. So this is the value of k that can fulfill this criteria of phase margin is equal to 30. From there, you can also compute the corresponding gain margin. Substitute again your phase crossover frequency using this newly computed gain for your proportional controller gain k. Substitute 0.05. Now you can compute the corresponding gain margin. Even though it is not asked in the question, sometimes the question will ask you to compute the corresponding gain margin. Your gain margin now is 2.58, which is greater than 2. Now you are in business. Your phase margin is 30. which is already satisfactory, and then your gain margin now is greater than 2, it is now already satisfactory. So with k 0.0, with k equals 0.7 here, you already fulfill the requirement of gain margin as well as the phase margin requirement. Okay, so that is what you have to go through for this type of design question. Okay, so that's it. Do you have any question? We don't have this. What do you mean you don't have this? No? I have just uploaded this note to your e-learning. You have this. You do. You have this note on your e-learning. Anybody else that don't have this note on, cannot find this note on your e-learning? Anybody else? Probably I'll go and double check that. Anybody else have any problem extracting these notes from e-learning? Anybody else? What the hell's going on here? It is there. Let me go to e-learning. Okay, let's go to my e-learning. There's e-learning there. Let's go to your e-learning. Log in. Let's go to my course. Section 3. Okay, all right. Okay, you don't have it, right? Notes 10-2. Okay, sorry, my bad. Section 4. You don't have it, right? Okay, don't worry about it. It must be my age is catching up. I really thought you already have it because I already upload this note for week 12. So don't worry about it. Okay, never mind. So this note here. So I will upload this note example 4.9. It must be my age. My age is catching up with me. Sorry about that. Okay. So I have also uploaded your assignment as well. Assignment 4. Where's your assignment 4? Is this note? So this is assignment 4. Make sure that you work on the first question of your assignment 4 before you enter your test 2. All right. Okay. Never mind. I'll upload my notes later on. Okay. Do you have any other question? Okay. So let us stop the class here today. So I will